Can you give me 5 minutes? In 5 minutes, I can make you an expert on our planet's energy choices. Okay, let's go.
So think about your day. Did you brew some coffee, charge your phone? Yeah, every single one of those things used energy. But where does all that power actually come from? And, with our world growing, will there be enough to go around? That's the huge question we're going to tackle.
All right, so here's our game plan for this explainer. First, we'll get the definition straight. Then we'll look at the fuels that are running the show right now. After that, we'll check out the alternatives, weigh the good and the bad of each, and finally, take a peek into the future.
Okay, let's start with the absolute fundamentals. Pretty much all energy sources fall into one of two big categories. And getting this difference is the key to understanding, well, everything else.
So, what's the bottom line? On one side, you've got renewable resources, the stuff we can use again and again because nature just kind of refills the tank for us pretty quickly. But on the other side, you have non-renewables. There's a limited supply, and once we use them up, they're gone, at least for any time frame that matters to us.
A really good way to picture renewable energy is like a circle, right? We use the sun's energy today, but that doesn't mean there's less sun for tomorrow. The whole process just keeps going. It's continuous, always replenishing itself.
But in total contrast, non-renewable energy is like a broken loop. It's a one-way street. We find it, we dig it up, we burn it, and that's the end of the line. That loop never closes because things like coal and oil took millions and millions of years to form in the first place.
Now, here's a super important detail. The whole renewable idea for some resources depends entirely on us. See, if our rate of consumption, how fast we're using something, is faster than nature can regenerate it, then even something we think of as renewable, like a forest, can actually run out.
All right, let's move on and see how this plays out in the real world. We're going to focus now on those non-renewable resources that, for better or for worse, are powering most of our planet right now.
When we're talking about non-renewables, we're mostly talking about these four heavy hitters. The first three, coal, oil, and natural gas, are what we call fossil fuels. And they're literally that, the fossilized, crushed-up remains of ancient life from millions of years ago. The fourth one, nuclear, runs on uranium, which is a specific metal we have to mine out of the ground.
This journey is a perfect picture of that one-way ticket we were talking about, and it has a huge environmental footprint at every single step, from damaging habitats when we extract it to pumping out pollution and greenhouse gases when we finally burn it for energy.
And wow, this chart really puts things in perspective. Based on how much we're using right now, some estimates say we've only got about 50 years of oil and natural gas left. Now, these numbers can shift a bit, but the main point doesn't change. These fuels are running out, and the clock is definitely ticking.
Okay, so if non-renewables are on a timer, what's the alternative? Let's switch gears and look at the really hopeful side of this whole story, the renewable revolution.
And what's cool is there are so many options. We can grab energy straight from the sun with solar panels, use the wind with giant turbines, or harness the power of moving water with dams. We could even tap into geothermal energy, which is literally heat coming from the center of the Earth, and biomass, which is just energy stored in things like wood or corn.
But hey, remember that rate of consumption point? This is where it gets really important. Some renewables, like solar and wind, are what we call non-depletable. No matter how much we use, there's always more tomorrow. But others, like biomass, are depletable. They absolutely need us to manage them carefully and sustainably to make sure they actually stay renewable.
So, with all these amazing renewable options, you might be asking, why haven't we just switched over completely? Well, let's take an honest look at the trade-offs that come with all of our energy choices. The reality is there's no perfect magic solution here, just trade-offs. Non-renewables are what we're set up for. They power most of the world, but they come with a huge environmental price tag and they're gonna run out. Renewables are way cleaner and won't disappear, but they come with their own set of challenges, like how big dams can change rivers, and it means we have to be really responsible managers.
And that leads us to our final and, honestly, most critical section. Where do we go from here? The future of energy is, without a doubt, one of the biggest challenges we all face together.
And this is why it's such a massive challenge. We've got about 8 billion people on this planet, and that number is going up every single day. The demand for energy is just huge. We all need it to live, so the choices we make are more important than ever before.
And to make it even more complicated, some of our most vital resources don't really fit into a neat little box. Things like water and soil. Yeah, they replenish naturally, but we can easily use them up way faster than they can recover. We can turn a renewable gift into a non-renewable crisis. Their future really is all about how we act.
So, I'll just leave you with this thought. Every single time you flip a light switch or start your car, you're making a choice. And as our big global family keeps getting bigger, how will the sum of all those millions of tiny choices end up shaping the world that we leave behind? Thanks for giving me 5. Make sure you like, subscribe, and comment.
Ever stop to think about what's actually powering your phone, or your car, or, well, pretty much your entire world? For most of us, the answer is this incredible story, one that started hundreds of millions of years ago, deep, deep under our feet.
So, how about this? Can you give me 5 minutes? I'm serious. In just 5 minutes, I promise I can make you an expert on the incredible and, yeah, incredibly complex world of fossil fuels.
We're going to start with the basics, what these things even are. Then we'll break down the big 3, coal, natural gas, and petroleum. And we'll finish up by looking at what the future might hold. Sound good? Awesome, let's get into it.
All right, section 1. So what are we actually talking about when we say fossil fuel? Honestly, the clue is right there in the name.
So you can basically think of it as nature's ultimate slow cooker recipe. Seriously. The ingredients? Ancient living things. Plants and swamps, tiny little organisms in the ocean. And over millions of years, they die, they get buried without any oxygen, and then they just cook under all this incredible heat and pressure. And what you get at the end is this super high energy fuel, which comes in one of 3 forms: solid coal, liquid petroleum, or natural gas. But here's the part that just blows my mind: the time scale. We're talking 100 to 500 million years ago. This is not something you can just whip up in a lab. You've got all this life dying and sinking. Then for millions of years, it's getting buried deeper and deeper, squeezed and heated by the planet itself. And only then does it turn into the fuel we use today. And that's the key, right? That's why we call them non-renewable. We're burning through millions of years of stored energy in the blink of an eye.
Okay, let's jump into our first type, coal. And you can't talk about coal without talking about the Industrial Revolution. It literally powered the whole thing. But get this, it's not just history. Today, this combustible rock still generates something like 40% of all the electricity in the entire world.
So how does a chunk of black rock actually light up your house? It's actually a pretty straightforward process, like a chain reaction. First, they mine the coal. Then they crush it into a superfine powder, so it burns way faster. That fire is used to boil water, creating this incredibly powerful high-pressure steam. That steam then gets blasted at a giant fan, we call it a turbine, and makes it spin like crazy. The turbine is hooked up to a generator, and it's that spinning motion that creates the electrical current that eventually powers your stuff.
So, like with a lot of things, it really comes down to a trade-off. On the plus side, coal is everywhere, and it's pretty cheap to get out of the ground. That's a huge deal. But the downsides are pretty major. It's the most CO2-intensive fossil fuel out there. Burning it also releases nasty stuff like sulfur dioxide, that's what causes acid rain, and nitrogen oxides, which create smog. And that's not even getting into the massive environmental and safety problems that come with the mining itself.
Okay, moving on to our next one, the invisible energy source, natural gas. You hear it called a bridge fuel all the time, right? The idea is that it's a cleaner step away from coal. But is it really that simple? Let's find out.
A huge reason we're even talking so much about natural gas is this one technology, hydraulic fracturing. You've probably heard it called fracking. And what it is basically is they drill way, way down into the earth, and then they blast a high-pressure mix of water, sand, and chemicals to literally fracture the rock. That cracks it open and lets all the trapped gas escape to the surface.
And this is where the dilemma really hits you. When you burn natural gas, it releases about half the CO2 as coal does for the same amount of electricity. That sounds amazing, right? A huge plus. But the main ingredient in natural gas is methane. And if methane leaks directly into the atmosphere without being burned, it's a way, way more potent greenhouse gas than CO2. So you add in the risks from fracking, like water contamination, and the fact that these leaks are invisible and super explosive, and suddenly that cleaner fuel label starts to look a whole lot more complicated.
All right, time for our third and final fossil fuel. And this is the one that really, truly moves our modern world. I'm talking about petroleum. You might know it as crude oil, or its nickname, liquid black gold. What's really wild about petroleum is just how everywhere it is. We all think about fuel, right?
The process starts by drilling for crude oil, but once they get that oil to a refinery, it becomes so much more than just gasoline, diesel, and jet fuel. We're talking about the asphalt on our roads, the plastics in our phones, our computers, our everything, even the fertilizers that help grow our food. It's woven into the very fabric of our lives.
So why oil? Well, its biggest advantage is simple. It's a liquid. That makes it super energy dense and really easy to move around and store, which is just perfect for things like cars, trucks, and planes. But the flip side is rough. We've all seen the heartbreaking images of oil spills and the damage they cause. And here's the other big thing. Oil isn't found everywhere. And for the last 100 years, the global struggle to control who has it has been a massive source of tension and conflict.
And all of this, it leads us to our final and maybe most important section. We've literally built our entire modern civilization on these ancient buried fuels. So what happens next? I mean, are we actually running out? Well, there's this really famous idea called peak oil. The theory goes that for any oil field, or for the whole world, production will eventually hit a maximum point, a peak, and after that, it's a downhill slide forever. Now, it's true that new technologies have kept pushing that peak further and further out, but they can't change the fundamental fact. There's only so much of this stuff in the ground. It is absolutely finite.
So let's take a look at who's sitting on the rest of it. When it comes to coal, the three biggest players with the largest proven reserves are the United States, Russia, and China.
Switch over to oil, though, and the map looks completely different. Suddenly, the top three are Venezuela, Saudi Arabia, and Canada. And seeing that list really helps you understand that geopolitical tension we were just talking about, doesn't it?
And finally, for natural gas, it's concentrated again. The biggest reserves are in Russia, Iran, and Qatar. So what you're seeing here is a clear pattern. These vital energy sources aren't spread out evenly. They're packed into just a handful of places around the globe.
So here's the big takeaway from all of this. Our entire modern world runs on these powerful ancient fuels, but they are finite, and they're not spread out evenly. And that reality leaves us with what is probably the single biggest question for our generation and for the next one. What is going to power our future? Hey, thanks for giving me 5. If this helped you get a better handle on fossil fuels, do me a favor and hit that like button, subscribe, and definitely drop a comment below with your thoughts on that final question. Today, we are talking all about one of the most powerful forces in our lives, the sun. So let's get right into it.
Can you give me 5 minutes? That's all I'm asking for. Just 5.
Because I promise, in that time, we're going to break down how we take pure sunlight and turn it into the electricity that powers our world, and what that really means for all of us. All right, here's our game plan. We've got 5 quick stops. We'll start with what solar power even is, then how we actually catch it. We'll look at the 2 different ways to use it, weigh the good versus the bad, and then we'll peek into the future. Let's do this.
Okay, first up, what exactly is solar power? Well, it all starts with the star of our show, literally, the sun.
So you know the sun? It's basically a gigantic nuclear fusion reactor floating in space, and it is constantly just blasting out this radiant energy, right? That's what we call sunlight. And the amount of power it's sending our way is just, well, it's hard to even wrap your head around. In fact, check this out. The sunlight that hits the Earth in just an hour and a half, just 90 minutes, has more energy than the entire world uses in a whole year. It's absolutely staggering. The potential is just massive. So all this energy is just raining down on us all day, every day. The big question then is, how do we actually catch it? How do we grab that sunbeam and turn it into something useful?
Well, the magic really happens in something called a photovoltaic cell, or you'll hear it called a PV cell. Think of these as the tiny little engines inside a solar panel. They're usually made of silicon, which, it turns out, does something really cool when the sun hits it.
So here's how it goes down. These little packets of light from the sun, they're called photons, they come flying in and bam, they slam into the silicon. That impact literally knocks electrons loose. And the cell is designed to act like a one-way street, forcing all those freed up electrons to flow in the same direction. And guess what that is? That's electricity, a direct current. From there, we just channel it through a circuit, power a light bulb, and the electrons loop back around. It's that simple. Light becomes electricity, just like that.
Now, when you think solar, you're probably picturing those high-tech panels on a roof, right? But that's not the whole story. There are actually 2 completely different ways to play the solar game.
So on one side, you've got passive solar. This is all about being clever with design. No machines, no wires. It's about things like putting big windows on the side of a house that gets winter sun, or building a roof overhang to create shade in the summer. It's just smart architecture. Then you've got active solar. And that's where the technology comes in, like the PV panels we just talked about. This is when you use equipment to actively capture and convert the sun's energy. So, one is about design, the other is about devices.
So, solar energy sounds pretty incredible so far, doesn't it? But, it's not a silver bullet. Like any tech, it's got its good sides, and it's got its not-so-good sides.
Let's start with the good stuff, because it's really good. First, the fuel source, the sun, isn't going anywhere. It's basically infinite. And while those panels are working, they're creating zero air pollution. No nasty particles, no greenhouse gases, and you don't have to keep digging up the earth for fuel like you do with coal or gas. It's pretty clean.
I know. It sounds almost too good to be true, right? Well, there is a catch, and it's a big one.
The single biggest problem is a word you're going to hear a lot: intermittency. It just means the sun isn't always on. It goes down every single night. So think about it. All day long, solar panels can be pumping out tons of cheap, clean power. But then, right as the sun sets, which is exactly when everyone gets home from work and starts turning on lights, TVs, everything, that solar power just vanishes. This creates a huge daily headache for the people running the power grid, a problem so famous it's even got a name: the duck curve.
So because of that duck curve, every single evening, other power plants, usually ones that burn fossil fuels, have to fire up like crazy to fill the gap. And that's not the only hurdle. Remember the silicone for the panels? Well, that has to be mined, and mining has its own environmental costs. Plus, if you want to build a really big solar farm, you need a lot of land, and that can sometimes mean destroying natural habitats.
So, with these pros and cons, where does solar actually stand right now? And more importantly, what's coming next? Okay, if you look at how we powered the world just a few years ago, you can see solar was, well, it was a pretty tiny piece of the pie. Only about 2%. Fossil fuels were still king. But here's the thing. This chart is already out of date because this story is changing faster than almost anyone predicted.
And the reason why? It all comes down to one thing: money. The cost to build solar has absolutely plummeted. Between 2010 and 2020, it got cut in half. In a lot of places now, it's actually cheaper to build a brand new solar farm than a new fossil fuel plant. And that single economic fact is changing everything.
And that leaves us with the final huge question. We know the energy is there. We know the cost is finally right. The technology works. The last great challenge, the final boss, if you will, is storage. Figuring out how to solve that intermittency problem, how to save that daytime energy for the nighttime. If we can crack that, can we finally let the sun power our entire world? Thanks for giving us 5. Please like, subscribe, and comment.
Can you give me 5 minutes? In 5 minutes, I can make you an expert on geothermal energy. All right, let's dive right in. Here's our roadmap for the next few minutes. We're going to cover what geothermal energy actually is, then how we turn it into electricity. We'll also look at where in the world you can find these plants, run through the biggest pros and cons, and finally, take a peek at what the future might hold.
Okay, so first up, what is this stuff? The name actually gives you a pretty big hint, right? Geo means earth and thermal means heat. So, yep, we're talking about earth heat. We're literally tapping into this giant natural furnace that's been humming away deep inside our planet for billions of years. At its most basic level, geothermal energy comes from the heat that's created by the slow, natural breakdown of radioactive elements way, way down in the Earth's core. You can kind of think of it like a giant planet-sized nuclear reactor that's been running safely for eons. And we're only just getting good at plugging into that awesome power source. And, this heat isn't just sitting still. It starts way down in the core and gets the molten rock in the mantle moving. Think of it like a huge, slow-motion pot of boiling water. These currents push that incredible energy up towards the surface. And in a few special places, that heat gets really close to us. That's the sweet spot we're after. Okay, so we have all this heat. But how do we actually turn it into electricity? The stuff that charges our phones and powers our lives. Well, the process is surprisingly clever. It all works in this really smart cycle. First, we send water down a pipe, sometimes for kilometers, deep into these superheated layers of rock. Down there, it's so hot the water instantly flashes into high-pressure steam. That steam then rockets back up to the surface, and we use it to spin a turbine, which, you guessed it, generates electricity. But here's the coolest part. We don't just let the steam go. We capture it, cool it back down into water, and then pump it right back down again to restart the whole process. It's a completely closed loop, and that's what makes it so renewable.
Now, this is a super important point because a lot of people get this confused. When we talk about geothermal power plants, we're not talking about the same thing as a ground source heat pump you might have for your house. Those systems just use the sun's heat that's stored a few feet underground. What we're talking about is true geothermal, drilling thousands of meters down to tap into the raw heat from the Earth's core, to literally boil water. So you might be thinking, if this is so great, why aren't these things everywhere? Well, it all comes down to one thing: location, location, location. Turns out, geothermal power is, well, it's a bit of a diva. It's incredibly picky about where it will work.
So could you build one in your backyard? The answer is almost certainly no. I mean, unless you live in a very, very specific kind of place, this just isn't going to be an option.
See, to make this work, you need a very special geological setup. You need to be in places where the Earth's crust is thinner and that hot magma is way closer to the surface. That's why you find these plants along places like the Ring of Fire or in Iceland. For pretty much everywhere else, you'd have to drill so deep to reach that heat that it would just be ridiculously, insanely expensive.
Okay, so like any energy source, this isn't a magic bullet. It's all about trade-offs. Nothing is perfect, right? And geothermal has a really clear list of pros and cons.
Let's start with the good stuff. The pros are huge. It's renewable and it has super low carbon emissions. But maybe its biggest win is that it's consistent. The sun isn't always shining, the wind isn't always blowing, but the Earth's core is always hot. It's a 24/7 power source. But the cons are just as big. We already talked about how it only works in certain spots, and the initial cost to drill and build a plant is massive. There's also a small risk of releasing some nasty underground gases if things aren't managed perfectly. So, we get the tech, we get the challenges. What does the future look like for this powerful, but kind of picky, energy source? And this really gets to the heart of it. Is this powerful energy source worth that massive price tag? I mean, we're talking about a huge upfront cost for drilling and building. But think about the payoff for the communities in the right spots. It could mean total energy independence with clean, reliable power for generations. It just takes a big investment, and honestly, a bit of a leap of faith to get started. So here's the bottom line. Geothermal isn't going to be the answer for the entire planet. It's just not. But for those lucky regions sitting right on top of a geological hotspot, it could be the perfect answer. An incredibly stable, clean, and long-term source of power. So really, the question isn't if geothermal works, it's where it works, and when we decide that huge upfront investment is finally worth it.
Thanks for giving me 5. Make sure you like, subscribe, and comment.
Can you give me 5 minutes? In 5 minutes, I can make you an expert on nuclear energy. All right, let's dive right in. Here's our roadmap. First, we'll get into the wild science of unlocking the atom. Then, we'll see how that science powers a massive atomic engine. After that, we'll weigh the pros and cons, the promise of clean energy versus the serious risks. And finally, we'll take a look at what's next for nuclear power.
Okay, first things first, let's get down to the absolute basics. I mean, how on earth does splitting a tiny, invisible atom release such an incredible amount of power?
So the most important thing to wrap your head around is this. We're not burning anything. There's no fire, no combustion like in a regular power plant. Nope, we're doing something way more fundamental. We're literally splitting the core of an atom. This process is called nuclear fission. Think of it like a mousetrap that's been set. All that energy is just waiting, and we're just giving it a tiny poke to release it all.
And this is where the magic really happens, the chain reaction. It's basically a game of atomic dominoes. See, one neutron hits a uranium atom, and boom, it splits, releasing more neutrons. And what do those neutrons do? Well, they go and hit other uranium atoms. This whole thing just keeps going and going. A self-sustaining reaction that unleashes a ridiculous amount of energy with every single split.
So you might be thinking, wait a second, if this is a chain reaction, why doesn't a power plant just, explode like a bomb? And that is a great question. It really boils down to 2 things, control and concentration. A bomb is designed to be an out-of-control, instantaneous reaction. It uses super concentrated fuel. But a reactor, that's all about a slow, controlled burn. The fuel is much less concentrated, and the whole point is to release that energy steadily as heat, not in one big bang.
Okay, so we've got the science down. Now let's look at the hardware. How does a reactor actually work?
Believe it or not, when you strip away all the complex stuff, a nuclear power plant is really just a super high-tech way to boil water. Seriously, just like a coal plant burns coal to make heat, a nuclear plant uses that controlled atomic chain reaction as its furnace. The end goal is the same: make stuff hot.
So inside that reactor core, you've got this little trio of components working together. First, you've got the fuel rods. That's where all the action, all the fission is happening. Then you have the moderator, which is usually just water. Its job is to kind of slow down the neutrons, get them to the perfect speed for the reaction. And finally, you have the control rods. These are the brakes. They're made of stuff that just loves to absorb neutrons. So by raising or lowering them, operators can hit the gas, tap the brakes, or stop the reaction completely.
And this is how that heat gets turned into the electricity that powers your phone. That intense heat from the chain reaction, it boils water, creating a ton of high-pressure steam. That steam then gets funneled to spin a giant fan, basically, a turbine. And that turbine is hooked up to a generator. As it spins, it generates electricity. It's almost exactly like a coal or gas plant from this point on. Oh, and you know those giant cooling towers you always see? That's not pollution. It's just steam, literally water vapor, as the water gets cooled down to be used all over again. Okay, so that's a lot of engineering. What's the point? Why go through all this trouble? Let's talk about the positives. Well, the upside is huge. I mean, first off, the energy output is just insane. One tiny uranium pellet, about the size of the tip of your pinky, has as much energy as a ton of coal. It's incredibly powerful. And here's the big one for our climate. Since you're not burning anything, there are no CO2 emissions at the plant. Zero. Plus, it's reliable. The sun isn't always shining, the wind isn't always blowing, but a nuclear plant can just keep humming along 24/7.
But, and this is a big but, there is of course a flip side to this coin. The risks are very real, and they're why this technology is so controversial.
Okay, let's get into the negatives. The first, and probably the biggest headache, is the radioactive waste. The spent fuel rods stay incredibly dangerous for like thousands and thousands of years, and we still haven't figured out a permanent solution for storing it. Then there's the fear of a meltdown. It's rare, for sure, but when it happens, it's absolutely catastrophic. And there are other environmental impacts too, like the hot water discharge affecting local rivers and lakes, and the radioactive waste left over from mining the uranium in the first place.
And really, you only need to say 3 names to understand the public sphere: 3 Mile Island, Chernobyl, Fukushima. These 3 accidents, more than anything else, have shaped how we all think about nuclear power. They're burned into our collective memory as proof of what can happen when things go horribly, horribly wrong. So, with all that in mind, where are we today? What does the future hold for nuclear power?
Right now, nuclear power accounts for about 10% of the world's electricity. That's a pretty significant chunk, coming from around 440 reactors spread out across more than 30 countries. But here's the thing. Most of those reactors, well, they're not spring chickens. The bulk of them were built decades ago. We're talking technology from the 70s and 80s. And now, they're reaching the end of their lifespan.
And that leads us to the big question we all have to face. Do we replace them or do we retire them? It's a huge decision. Do we pour money into new, hopefully safer and more efficient reactor designs? Or do we say, you know what, it's not worth the risk, and go all in on things like solar and wind?
So the future of nuclear really isn't just a science problem. It's a huge balancing act. You've got these massive challenges: what to do with the aging reactors, how to finally solve the waste problem, and how to earn back public trust. But you also have these incredible opportunities: developing new, safer reactor designs and getting that reliable, carbon-free energy we so desperately need. It's all about weighing those pros and cons.
Back in the 1950s, everyone said the future was atomic. Today, the question is, well, is it still? There's no easy answer, but now you understand the science, the technology, and what's at stake. Thanks for giving me 5. Make sure you like, subscribe, and comment.
Can you give me 5 minutes? In 5 minutes, I can make you an expert on hydroelectric energy. Welcome to The Explainer. Today, we are diving deep into one of the oldest and honestly one of the most powerful forms of renewable energy on the entire planet. Here's how we're going to break it all down. First, what is this stuff? Then we'll look under the hood of a dam.
We'll also tackle a huge environmental question. What happens to the fish? After that, we'll weigh the good against the bad. And finally, we'll peek into the future of hydropower. Ready? Let's go.
All right, first things first. What exactly is hydroelectricity? And, how big of a deal is it really?
So at its heart, the idea is incredibly simple and it's powerful. Humans have been using this concept for centuries, from grinding grain with water wheels to powering our entire modern world. The sun does the work, evaporating water that falls as rain, flows into rivers, and all we do is capture that motion. It's a beautiful, natural cycle. Now check this out, because this is pretty surprising to a lot of people. We hear all the time about wind and solar, right? Well, it turns out that hydropower is, by a long shot, the single largest source of renewable energy on the planet. It's kind of the quiet giant in the room.
So how in the world do we actually capture all that power from a river? Well, the most common way is with a big old dam, or what engineers would call a water impoundment system. The easiest way to think about it is like a giant controlled waterfall. First, you have the reservoir, which is basically an artificial lake storing all that water. That's your stored up potential energy. Then, a huge pipe called a penstock guides that water down toward a turbine. The sheer force of that water spins the turbine, which is hooked up to a generator, and boom, you've got electricity. This whole four-step process is what gives the operators such precise control. And honestly, this is hydro's superpower. Because they can control the water flow, they can control the electricity output, like second by second. That makes it unbelievably reliable. But, okay, let's be real. Building a massive concrete wall across a flowing river, well, that's obviously going to have some serious consequences for the creatures living in it. And this is a huge problem, especially for species like salmon. I mean, these fish have this incredible instinctual drive to travel hundreds of miles upstream, back to the exact spot where they were born so they can reproduce. A giant concrete wall is, well, it's a pretty major roadblock.
But this is where human ingenuity is just so cool. To solve this, engineers have come up with some pretty wild solutions. The most common is a fish ladder. It's like a series of small cascading pools that fish can literally jump up. But then there's my personal favorite, which has been nicknamed the salmon cannon. It's a flexible tube that uses gentle pressure to just whoosh, shoot the fish right up and over the dam. It is a real thing, and it is absolutely amazing.
Okay, so obviously, like any massive infrastructure project, building a dam comes with some really serious trade-offs. We have to weigh the benefits against the drawbacks here. And it really is a trade-off. On one hand, you get super reliable, clean electricity once it's up and running. Plus, you get things like flood control and new spots for recreation. But on the other hand, the upfront cost to build one is astronomical. It floods huge areas of land, forcing people to move and destroying habitats. And here's a weird one. All the plants that get flooded and decay at the bottom of the reservoir, they release methane, which is a really potent greenhouse gas. So, with all of that in mind, what does the future actually hold for this incredibly powerful energy source? Well, modern hydro projects are being built on a scale that is just, it's hard to even wrap your head around. The Three Gorges Dam in China is the largest power station of any kind on Earth. To create its reservoir, they had to move so much water that the shift in mass literally, and I mean literally, slowed the Earth's rotation, just a tiny, tiny bit. That's the kind of power we are talking about. But its future might not just be about getting bigger, but about getting smarter. This is where it really earns its nickname as the guardian of the grid. See, we're relying more and more on power sources like wind and solar, which are great, but they aren't available 24/7. Hydro can fill the gaps instantly. Wind stops blowing, a dam operator can ramp up power in seconds. Some plants can even use cheap excess electricity at night to pump water back up into the reservoir, turning the whole thing into a massive rechargeable water battery. And this leaves us with a really important question for our energy future. As we keep adding more solar and wind to the grid, is it possible that the instant-on, super reliable nature of hydropower will make it the absolute essential backbone that holds our entire clean energy system together? Definitely something to think about. Thanks for giving me 5. If you learned something, make sure you like, subscribe, and comment. So when you think of renewable energy, I bet those giant spinning blades are one of the first things that come to mind. Today, we're going to harness that power and figure out exactly how it all works. Hey, can you give me 5? Seriously, in just 5 minutes, I'm going to make you an expert on wind power. First, we'll take a quick trip back in time to see where it all started. Then we'll dissect a modern turbine to see what's inside. After that, we'll follow the journey from spin to spark, how it actually becomes electricity. Then we'll check out the difference between wind farms on land and out at sea. And finally, we'll wrap up by weighing the pros and cons. You ready? Let's do this. All right, part 1, a little history lesson. You've all seen those old kind of quaint windmills on farms, right? The ones that creak in the wind? Well, they might look pretty low-tech, but believe it or not, they're the direct ancestors of the giant turbines we see today. So what's the big difference between then and now? It's really all about the mission. We've gone from using wind for pretty simple mechanical jobs, like pumping water for cattle, to harnessing it on a truly massive scale. We started with some of the first wind farms out in the California desert, and now we've got these modern giants that are powerful enough to light up entire cities. Which brings us perfectly to part 2. What exactly are these incredible machines? Let's get right in there and take a look inside a modern wind turbine. Okay, so the main parts are actually pretty simple to grasp. You've got the super tall tower, obviously for height. You've got the blades, which catch the wind, and the rotor is just the hub that holds the blades together. Now see that big box at the very top? That's called the nacelle, and inside that's where all the magic happens with the generator and the gearbox. But here's a little secret. The real genius behind how this thing works isn't in that box. It's all in the shape of the blades. And this is where things get really cool. See, the blades aren't just giant, flat paddles pushed by the wind. No, they're much smarter than that. They're actually shaped just like an airplane wing. It's a design called an airfoil. So as the wind flows over that curved surface, it has to travel faster over the top than the bottom. This creates a pressure difference. Lower pressure on top, higher pressure below, which generates a force we call lift. It's literally the exact same principle that lifts a 747 off the ground, except here, it's turned on its side to create that powerful rotation. Okay, so now we've got the blades spinning like crazy. But how does that spin become the electricity that powers your laptop or your TV? Well, that's what we're jumping into right now in part 3. Now check this out, because this is where the mechanical magic happens. Those giant blades, they're actually turning pretty slowly, around 18 revolutions per minute. I mean, that's nowhere near fast enough to generate any serious electricity. So inside that nacelle we talked about, there's a gearbox. Think of it like the gears on your bike. It takes that slow, powerful rotation and multiplies it by 100 times, ramping it up to a whopping 1,800 RPM. And that high-speed spinning is what it takes to get the generator humming and pumping out electricity. So this leads to a pretty obvious question, right? If it's all just about spinning a generator, why on earth do these things have to be so mind-bogglingly huge? Well, the answer is actually pretty simple. It's all about the wind. The higher up you go, the stronger and steadier the wind blows. So by building these towers so tall, they're just reaching up to where the best wind is. And get this, their huge blades sweep an area larger than an entire football field. So more height plus a bigger sweep area equals a ton more captured energy. Okay, that brings us to part 4. We know they're huge, but where do we actually put these giants? Well, we've got 2 main options: onshore, on land, or offshore, out at sea. Let's compare the 2. Onshore farms are probably what you picture. You see them dotting the landscape in really windy spots, like the wide-open prairies of Wyoming or across desert mountain passes. That's the established tech. But the really exciting new frontier, that's offshore. By building these farms out in the oceans or even the Great Lakes, we can tap into winds that are way more powerful and way more consistent than almost anywhere on land. And here's why offshore is such a potential game changer. Think about it. More than half of the entire U.S. population lives within 50 miles of a coast. So putting wind farms offshore means we can generate enormous amounts of clean energy right on the doorstep of the big cities and population centers that need it the most. It's super efficient. All right, we've made it to our final section, part 5. Let's zoom out and take a balanced look at the big picture, the good and the things to consider. So the pros are pretty huge, right? It's clean energy, it's totally renewable, and it doesn't pump out greenhouse gases. Plus, it's reliable and helps with energy independence. But on the other hand, there are definitely things to think about. You can't just stick a wind farm anywhere you want. You need the right geography with a whole lot of consistent wind. And as we've already covered, these are incredibly large and complex machines to build and maintain. But to really put its power into perspective, just look at this number. Even a small wind farm, we're not even talking about the huge ones, can generate enough clean electricity to power more than 9,000 homes. I mean, that is a staggering amount of power from one renewable source. It really shows you why wind is such a critical piece of our clean energy future. Thanks for giving us 5. Like, subscribe.